today is to give a short presentation of OVGU in my chair, and after that we will have three scientific discussions, three scientific presentations of my research staff. They are going to present their respective research topic, and then yeah, we have a discussion. So in general, if you have any questions, please feel free to ask at any time. We are doing online lectures for 1.5 years now in Magdeburg, and I don't really like it because I don't get too much interaction with the students. They don't ask very much, and I don't see if they understood. So please, if you have questions, simply unmute your microphone and say something. Okay. So the Otto von Guericke University is quite young. We exist since 1993. Before that, there used to be 3 different universities in Magdeburg. One was a technical university, which now is the main campus. There's also a college of education, which is now the faculty of social science. And finally, there's a medical campus that also used to be a own university before 1993. And in 1993, all of these universities merged to one single university, which has the name Otto von Guericke University now. And if you have the possibility to come to Magdeburg, you will probably be a little bit irritated because everything is called Otto von Guericke. Not only the university, it's really almost everything. Additionally, in the Middle Ages, we used to have an emperor that also has the name Otto. So really everything is called Otto except the soccer stadium. That has some other. Okay, the OVGU today has around 15,000 students. So we are, let's say, in the middle of the German universities. The biggest university is in Aachen, which has around 45,000 students, and there are also much smaller universities in Germany. So each year we graduate around 2,500 students, and right now 1,600 people are writing a PhD dissertation in Magdeburg, in all of these 9 faculties. Yeah, so here you see a map of our main campus. Yeah, you see it. The map of our main campus is the city center, so it's not as big as the UFSM campus because we don't have a lot of space, but nevertheless it's quite nice. And I highlighted a couple of special buildings. One is the building of our faculty, the FITE, our Faculty for Electrical Engineering and Information Technology. In building 9, this is where my office is. This is where most of my staff members are located. And then there are a couple of other important houses, like our canteen, where you get horrible student food, and the library, of course, and the OLZ, which is for computers and so on. Also, the north you see the North Park, a very nice park for recreation, where you can do some sports, for example, or have a barbecue, and so on. It's used very often by the students in the university. And here are some impressions of the university. So the main entrance, very nice. Located, and we have some nice architecture. Here on the bottom you see the library. So very nice architecture. This is taken directly from Cantina to the library. Finally, our building on the right hand side, it looks a little bit like a prison, but in fact it's quite nice. And on the top level, you see one of our labs. This is our SCADA system that we now are operating since 2018, which was funded by DFG. So you see we are power systems and the planning and control of electric power systems. And we want to do this on an industry level. So therefore, we bought a SCADA system that also is operating at transmission and distribution system operators. So this is commercial software from the German market leader, PSI, and the students and the PhD students will be educated on exactly the system that is also used by the TSOs. So let's have a short look on our Faculty of Electrical Engineering, Information and Technology. You see these, this faculty consists of four institutes. We used to be 5, but a couple of years ago, one institute was closed and merged into the other institute. So now we are 4 institutes, one of automation technology, one of information technology and communication. My institute is the Institute of Electric Power System, and finally we have an Institute of Medical Engineering. And you see the names of the chairs down there, so I will not read every chair, but we have around 20 professors. Some are junior professors, like Ines Hauer, for example, in my institute was responsible for electric energy storage systems. So if we come to talk about the Institute of Electric Power Systems, you see we deal with electric drives, we deal with renewables and power grids. That's my chair. And we have a junior professorship for storage systems, and finally a chair for power electronics. So from now on, I'd like to talk a little bit more about my chair of power networks. So this is the LENA chair. And here you can see an overview of the LENA chair. So we are organized in 5 different groups, and each group has, of course, a group leader, and one of the group leaders is here today. Christian Klabunde will also present a little bit of topics he's dealing with in the grid planning and operation group. Additionally, the energy storage group is led by Professor Ines. We have a hydrogen group, and from the hydrogen group, Christian Rinne is here today. He will also give a presentation on the work on hydrogen. Now we have a group on assets. Actually, Marc should be here and give a presentation about that, but unfortunately, he's ill today and could not give this presentation. And finally, the group Energy Market and Renewables. And from this group, we have Tahaguas Woldu here, who will also present a little bit on modeling of wind energy sources and power system transits. Yeah, so in fact, there are 20 researchers at my chair, and 6 external PhD students. They work at industry, but are linked to the chair by a project, for example, and can also write a dissertation. Now we have some assistant lecturers. I do not do all of the lectures on my own. We have some special experts who present some special topics. And we are spread all over the campus. So I already said Building 9 is our headquarters. But we have also offices and labs in Building 3, Building 10, and Building 11. In Building 11, we have a special high voltage current lab that is now set up right now. And on the right-hand side, you see that we are cooperating with a couple of universities in Germany and abroad. And one new university will be University of Santa Maria. So we are planning to do nice projects together, and then UFSM will also be on this prestigious list here. And we also cooperate, of course, with a couple of industry in Germany, mostly big company names like Siemens or PSI, and our main cooperation partners are transmission and distribution operators. Now we have founded one company, Delico Engineering, who's dealing with hydrogen. As I said, Christian will probably present also a little bit about dealing with engineering. And in Magdeburg, there's the Fraunhofer Institute for Industry Automation, and of course, we also cooperate with them. So let's talk about our research focus. And our specialty is to have a holistic point of view of the entire electric power system. So what are the players in the power system? What drives them? What are their restrictions? And especially, how do they cooperate and interfere? And how does this interference affect the grid? And are there any problems that come from utilizing the grid, like congestions or voltage problems? And then how do we solve these problems? So this is in general a description of what we are doing. And to do that, we need optimized models of the grid in all time frames, so for the steady state, for the quasi-steady state, and for the transient state. And we develop these models, we optimize these models, and by that we are solving the problems of transmission and distribution system operators. So we start in the operational phase, and if you find out that it's not sufficient to solve all of the problems on the in the operational phase, we also proceed to the planning phase. How can we extend our grid in such a way that the existing problems and the foreseeable future problems are used as efficient as possible. Problem is, if you want to build a new power line in Germany, it takes between 20 and 40 years, because all of the people are against it, and you have to fight in law in court to get these lines and have a lot of discussion with people. When you get your power line, you don't need it anymore, you need actually a bigger one. So the grid is always behind the actual need, so therefore it is really, really important to operate the grid as efficient as possible. And the main point to make the grid operation efficient is knowledge of the grid state. And especially in the low and medium voltage grid, there is almost no measurement equipment. So we don't know how the grid state actually is. So therefore, grid state identification is also one big topic at my chair. I started on this topic when I was a PhD student myself. I did work with a distribution system operator together on ideas how we can infer on the grid state. This means we don't need the exact grid state. This is too costly, so it should be cheap. And the distribution system operator only wants to know, do I have a problem or not? So we developed methods to say there might be a problem or there's definitely no problem. It can be quite calm and do nothing, but if there might be a problem, we should have a closer look and find out if there's really something you need to do. So still, this is an ongoing research at the DSO level, because when there's more wind and PV coming to the low and medium voltage grids, the problems get worse. And still we don't have measurement. And also there's a smart meter rollout. There's a legal problem to use this data, because the European regulations said that personal data cannot be used in other ways, only for accounting. So therefore the grid operator is not allowed to use smart meter data, although the smart meter data is available. So we still need these methods. So this is the second bullet point. Data is also extremely important for grid operation and the knowledge of the grid state. Of course, we also deal with the integration of renewables, but we do it from the grid perspective. So how can we include renewable sources into system operation processes, for example? How can we make them as grid neutral or even grid supportive as possible? And the newest trend is to have grid forming PV systems. So we also deal with all of these kinds of aspects and develop perspective models. And finally, the fuel cell group and energy storage group, and also deals with e-mobility. So we have a quite old e-car. It's not as nice as yours. It's one of the first generation. Still has a gearbox, but it's quite funny to drive around this this car. You can see it. So this red car is our e-car first generation. It still makes fun to drive. And, the topics are how can we implement charging infrastructure, how is the charging infrastructure interfering with the grid. Now, are there any special things to consider, like congestions, for example, voltage problems? How is charging of a fleet managed to be as grid neutral as possible? And can we get ancillary services out of electric vehicles, especially fleet of electric vehicles? And finally, this will be part of the presentation of Klabunde transmission technology. So there's a big discussion in Europe whether to use overhead lines or cables. So people don't want to see a power system infrastructure, so why not go underground? But people also don't want to pay for grid infrastructure, but cable is more expensive than overhead line. And so we are talking with the transmission system operators, what are the options. We are talking with the people and explain to them what are the differences, what can you expect, are there magnetic or electric fields, and do you have to be afraid of power lines or cables and so on. And on the transmission system perspective, there are congestions in the system, and there are some parallel lines that are not congested at all. So we need to operate this grid more efficiently, for example, by rerouting power flows. And this can be done by power flow controlling assets like phase shifting transformers or HVDC lines. And this is the topic of Christian is going to present now what types of flows we see in the European internal market and how we can change them and make them better in such a way that the system is not overloaded. Okay, so these are our research topics. And almost the final slide is, I have to give some lectures too. And here you see the list of lectures that is given by my chair. The other three are a bachelor course. So you see we are mostly dealing with students in the master course. So in the bachelor course, of course, you get some knowledge of fundamentals. What types of assets do you have in the grid? How do they work? Some very, very basic calculation of the power system. In the master course, we do professional grid calculation, power system analysis on the steady state and quasi-steady state side, and also power system dynamics. There are a couple of special lectures on renewable sources, wind energy, PV systems, and so on, in German and in English, of course. So we have a German master program and an English master program. And there are some other special lectures like storage systems by Professor Ines or power system operation. We are the only university in Germany, I guess, who offers such a course. And this is because before I went back to the university, I worked in power system operation at one of the German transmission system operators. And we have in one of the lectures live streamed to the control room of 50 hertz, and they show the actual grid state and what's going on, and give a presentation on what they do at 50 hertz and what system operation is and so on. So this is really interesting for students, also a nice way to find a company, for example, for writing their master thesis. Yeah, so that's pretty much it. Thank you for your attention, and I hope I have the chance to see you in person one day, and maybe in Magdeburg. So why not? Okay, thank you. Are there any questions?
Okay, if nobody has a question, I think I feel obliged to respect to the nice presentation to have to make a question.
Yes, please.
Here is Professor Humberto. It was nice to hear about your university, and since we have some graduate students that are addressing the issue of grid forming inverters and looking into this problem, I noticed that you have a group over there that is addressing the same topic. Could you mention a little bit about the work that have been done regarding to changing the way that converters, DERs, distributed energy resources, are being connected to the grid instead of the former grid following to the new grid forming way of connection?
We are still in a, let's say, simulation phase. Yeah? So there is some discussion in the standardization groups at RWE, for example, or IEEE. Also there are some working groups in IEEE where Christian Ziegler is working on to define.
Maybe in the integration and renewable energy group, there is some work have been carried out. Who is the professor that? Who is the in charge of head of this group integration of renewable energies over there?
It's divided in two groups. So when you talk about the power electronics, this would be Andreas Lindemann, who is in charge for the control of power electronics. And if you deal with grid integration, this would be my part.
Okay, good, excellent. Thank you very much.
Okay, so I guess it's time to hand over to our next presenter. Maybe we start with Christian. Yeah.
Okay, so yes, welcome to my presentation. So first of all, I want to thank Mr. Professor Daniel for the invitation to the University of Santa Maria. And today I want to present some of my research topics at the chair for electrical power networks and renewable energy. Yes, first of all, I'm not an electrical engineer. I studied business economics and worked since 2014 as a chair for Professor Wolter. And in 2014, I also have founded a company contributing, like Mr. Wolter introduced in this presentation. And yes, I have three parts of our presentation. First of all, I will tell you something about our actual project for reversible fuel cells. Then I will tell you something about our startup, engineering, where we develop diagnostic tools for electrochemicals energy converters. And the last part of my presentation will be on my PhD topic, energy markets designs. Yes, so let's start with my first topic, reversible fuel cells. On the right-hand side of the slide, you can see the actual test bench of a PEM URC fuel cell. My colleague, Mr. Rinne, have built it up in our laboratory in Magdeburg. And PEM fuel cell is a polymer exchange membrane unitized reversible fuel cell. So the reversible fuel cell have one big advantage. So you can do a fuel cell mode and electrolyzer mode in one system. So you have one periphery component for the system, so you don't need one electrolyzer and one fuel cell and operate them separately. You can include it in one system. And in the project Reflex, it starts in 2019. We built up this test bench, and the name of the project is Untitled Reversible Fuel Cells for Flexible Energy Storage. And let me say something about the topics into the project. First, building up the test bench was really a complex work, and then we develop and investigate a catalyst for catalyst material for the PEM URC. The catalyst into the membrane have to work on both sides. So you have to produce hydrogen, the electrolyzer mode, and produce energy in the fuel cell mode. And then we develop and testing a stack with 5 cells and electrical power from 1 kilowatt. This was the topic, and we investigate the switching process between electrolyzer and fuel cell mode. And I think this was the most difficult topic in the process, in the project, what we had, because you have on the one hand side you have oxygen and you have hydrogen mode on both sides, and you have in the electrolyzer mode you have water side and oxygen side. So this was really difficult to manage the switching project into the cell. And my topic on the economic side was techno-economic analysis and development of business cases for this PEM fuel cell for systems. So let me show you some use cases for this PEM fuel cell. There are flexible energy storage opportunities for the systems, like sector coupling. You can couple some sectors with it, maybe the heating network, the electric grid, or the natural gas network or hydrogen network. And the fuel cell, the reversible fuel cell, is able to work with all these networks. On the right side, on the top of the slide, you see the opportunity or the use case of energy storage and demand side management for the grid. So you have the opportunity to save energy by the reversible fuel cell with hydrogen. So if there are too much energy, too much load into the grid, you can take some load out of the grid and save the energy into hydrogen, and then you can use the hydrogen with the same system and get back to electrical load. Yes, and on the bottom side of the slide, you see two use cases for the decentralized energy productions. The first one is the CHP system for apartment buildings or for private buildings. The idea behind that is you can use PV or solar energy on your rooftop of the building, and then you can save it into hydrogen. And when you need the electrical loads, the electrical power, you can bring it back to your house with the hydrogen and the fuel cell node. So this is the main advantage of the system, that you can use it in both directions. And the last one I want to present is a UPS system or APU system, so an uninterruptible power unit or ancillary power unit. So you can load the system, or the system can load it by itself and can produce energy at the moment when you need it. Okay, now let's go to the next slide. My next topic is my company, Digital Engineering. I founded this with the fuel cell group from the OVGU, from the LENA, and we founded it in 2014. And we developed diagnostic systems for fuel cells, electrolyzers, and redox flow batteries. The first product I want to show you is the DVP cell voltage system. It's a measurement device to monitor electrochemical energy converters. A fuel cell or electrolyzer have single cells that are connected into a row, and with this system you can contact every single cell and monitor it. So when any cell have a low voltage, you can see it, and over the system control you can change the voltage so the whole stack of the system didn't get damaged. The second one is for research topics. It's a DVP current density measurement system. It's a temperature and current measurement system for the inside of the fuel cell or electrolyzer. Here on the pictures on the bottom of the slide, you see some sensor layers from that we have developed individually for our customers. On the left side at the bottom, you see a sensor layer with about 200 sensors, 200 temperature sensors, and 200 current sensors. All of it is bring under multi-layer sensor layer. In the middle, you see a test bench from the Baltic Fuel Cells Gebhardt from Germany. Into it, a sensor layer from DVQ Engineering. This is a test bench for single cell testing. And on the right-hand side, you see a graphic when you monitor with this measurement devices. So this is one of our topics by DVQ Engineering. We may develop a measurement device, and on the other hand side, we make engineering services for the industry in Germany. Let me show you some three examples. On the left side, we built an energy pavilion for the Gas GmbH. It's a company who provide or operate a natural gas network and want to know how they can transport hydrogen in the future in their networks. And we built up this energy pavilion, introduce a CHP system which operate with pure hydrogen and provide the pavilion with energy, heat, and in the summer also with cooling, also cools the pavilion. In the middle, we developed, or my colleagues developed, a hydrogen UPS system. This was also in the project with LENA. There is a PM-based UPS system with 1.5 kilowatts electrical power, and therefore you can use the system for an independent power supply over 72 hours. The last one is the Taylor system for the Fraunhofer in Magdeburg. There is a HAL system into it, so a hydrogen electrolyzer and fuel cell system, and this was for research topics for the Fraunhofer in Magdeburg. Okay, my last slide from DICO is a really nice project that starts in September this year. It's about energy management system for controlled charge for electrical vehicles for apartment building, and therefore we work together with some local companies in Magdeburg who want to charge electrical vehicles for their customers with decentralized produced energy. from a fuseled Chp system. You see it on the left top of the slide. There we have a Chp system with the electrical power of 4.2 kilowatts, and then we have a terminal power of 7.5 kilowatts. So this is for the base load for the building. Then we have a solar plant, solar energy plant on the rooftop of the building with around 40 kilowatts peak. This is not pure safe, we're just modeling the best electrical power for this, and then we save the energy in the battery when it can be used by the charging points. You see it on the right side of the slide, and therefore in the middle of this concept is the energy management system. And the main challenging part of this is to communicate with all of these different users or partners in the system, or devices in the system. So we have a connection to the grid, we have a connection to the Chp system, we have a connection to the AC converters of the solar power plant, we have a connection to the load management system of the charging points, and we have a backend and front-end server where the parties in the apartment building can use a mobile app and have a calendar there and have a look. Okay, when can I charge green energy, when I can charge heat, when I can charge parts, and then they can choose the optimal point where they want to load or charge the electrical vehicles. And one of the main topics is that the energy management system is able to communicate with the local network. So we have a partner as a local electrical grid operator is also in the project. And we want to communicate the energy management system with the local network. So we have a good operation point in the network. Okay, really interesting project. Okay, now let me go to my last slides. This is about my PhD topics, the challenges for future energy market designs. And firstly, let's have a look on the graphics on the left side of the slide. There are two graphics. First of all, the graphic A. This is price building in a sacrosanct situation of the grid. And then at the bottom of the graphic, you see the merit order. And on the left side, you have all the renewable energies, because the merit order is built as a marginal cost of the next kilowatt hour that has been produced. And so you have the Sarkozy ran over the last slide of the last line of the supply curve, and then you got on the left-hand side equilibrium price. This is under the upper limit. In Germany, at the spot market, we have an upper limit for a megawatt by 3,000 euros, so it's the upper limit. So we are protected by really, really high price peaks. So at the left, we have the price, the equilibrium price under the peak, under the upper price limit, and on the right-hand side, you see when the price increases, or the capacity is not enough to provide all the electricity, you have a price. This is over the equilibrium, and so you have a missing money problem. So there are there are missing investments into capacity, so the price increases really, really high, and so it's better from an economic view that there are investments in more capacities, so to provide the capacities to the customer, and then on the right hand side on the graphic B, this will be able that the equilibrium price go down to the upper limit price. And so we have a welfare increase, yes, at this point. So the market design, the future market design is about to secure the generation adequacy, and due to risk aversion of the investment decision makers of power plants, it comes to the missing money problem, because the investment range of the decision makers is about 50 years, and mostly they behave risk averse, and so it's come to the missing money problem. So this is a problem because the welfare losses due to this problem can be really large. So we have to discuss other market design that we can use in other designs in the energy market only market to avoid these problems. Okay, let's go to my last slide. It's about a project that starts at the beginning of 2021 at the LENA, the project Untitled in English. And in English it's called grid stability through instantaneous reserve with virtual sourced dominated grids. So we have the point that we have more renewable energy integration into the grid in Germany due to the energy transmission in Europe and Germany. So we have less synchronous generators and grid that can provide the instantaneous reserve. Therefore, we have on the economic side, on the market side, we have a problem because the instantaneous reserve is free at the moment. So the synchronous generators can provide it, and in the future, it's now possible when we have no more coal energy plants in Germany till later than 2035. So we have a problem at this point, and in this project we have a look on the grid side. My colleague Mr. Klabunde work on this topic, and I work on the economic type of topic. Therefore, we have to create investment incentives to provide this instantaneous reserve. One considering is to use capacity remuneration mechanism to do this, and the actual status, the current status of the project is that we maybe combine the instantaneous reserve market with the primary energy market. So, and I will show you on the right side of the slide one idea to design the supply and demand of inertia at the market. So the blue line in this graphic is the non-discretionary inertia demand. So this is the demand of instantaneous reserve or inertia that we need to operate the electric grid. Yes, so this is absolutely unelastic. This is the point, the inertia that we need. And then it is possible that due to specialized events in the electric grid, there are more demand on inertia. So the green line shows this demand, and the red line shows the global inertia supply. So now it's a question how we give this price. And we can provide the non-discretionary inertia demand with a fixed price. And then we look, okay, when we have a situation in the grid where the more amount of inertia increase the use of the network, and then the marginal cost of this use can be the price for the more inertia that the providers of instantaneous reserve will provide to the system. And so this is a possibility to make a price mechanism to have a price for a product that is actually free. So this is something that can go to my PhD topic, and this is slide I will end my presentation. And then I want to say thank you for the attention, and if there are any further questions, yes, I'm here for the questions, and please ask. Okay. This is a question.
Actually, it was a quite interesting presentation. Thank you very much. I appreciate very much. I feel that you are addressing different issues, but somehow seems to get it connected. So the question that I would like to make you is regarding the last topic, how to connect it with, what's the role of hydrogen generation in this inertia demand for increasing the stability of power system?
Yes. Okay. Yeah. The topics was a little bit separated, but there are also possibilities to connect hydrogen system with inertia. So when you produce energy with fuel cells, you can also maybe with the DC converter provide inertia, and also there's a topic maybe the points to the mnemonic problem. So you are able to change the demand side management with hydrogen energy storage due to fuel cells and electrolyzers. Then you can change the demand curve of energy supply also on inertia. So you can, yes.
Yeah, interesting, quite interesting. Another issue is this one. I was kind of surprised with the UPS that you have designed, because it has a unusual high autonomy in terms of energy, 72 hours. However, the power is it's not it's 1.5 kilowatt, and then if you look for a regular UPS 1.5 kilowatt, of course it is smaller. So, but anyway, what kind of application do you think this is promising? They have this high autonomy and not that high power. And then how do you see the, getting this hydrogen UPS in a regular market of lead-acid battery or even ion lithium battery?
So the hydrogen systems that I presented was mostly for standalone systems, like maybe mobile functional systems that have not grid access. So you can use the hydrogen or maybe the reversible fuel cell to produce energy for the standalone system what doesn't have grid access. And then there is this mass when you have 1.5 kilowatt hours for kilowatt power to provide this when there is
And another question that I would like to hear, just to finalize on this issue, how about the reliability compared with lead acid and ion lithium batteries?
With each batteries, yeah, at the moment it's a point, I hope I understand your question right, it's a point that the lithium batteries at the moment is a cheaper opportunity to provide this energy. So this is something I didn't say in the presentation, the reversible energy and also the fuel cell and electrolyzer technology is at the moment it's too expensive. So I think in this decade it's possible to use, economic view, it's better to use lithium-ion batteries. But I think about after 2030, we are at the point where we scale up the technology so high that it's possible to compare with lithium-ion batteries due to economic views.
Interesting, quite interesting. Just to finalize over here, Professor Mario Martins is a professor from mechanical engineering, is within the room here, and then he also is using hydrogen but in a different kind of application for mobility, and then maybe he can explain a little bit better on this one.
Hello. Thank you for the wonderful presentation. As Professor Pinheiro is saying, we use hydrogen in a more conventional way. We use it in internal combustion engines. So we have an ongoing project now to have it applied for mobility on a very standard way of burning it into internal combustion engine, which in one way seems to be very standard, but on another way, it means that we have several challenges regarding combustion control and keeping at high levels of efficiencies with all challenges that hydrogen gives us, alongside the benefits of potentially very low and ultra low or even zero emissions, depending on the level of NOx emissions that combustion will give us. But this is what we are doing now. We are focusing mainly on mobility, but also opening a way for power generation from a more conventional energy supply.
Yes. Okay. Where did you focus on the mobility for personal transport or for heavy duty transport? The state of the art at the moment we have in Germany, hydrogen is actually because due to efficiency problems and the weight. It's really interesting in the part of heavy duty transportation in the mobility sector. So it's the same that you see here.
Yes, we are researching for light duty transport, but we know that the main application would be for heavy duty transport in a way that we are not so constrained by mass and size restrictions, volumetric restrictions. But on the other hand, we see it as let's say a more immediate alternative to decarbonize and to depollute urban centers than going straight to battery electric vehicles. That would open a small niche, we think, even on hybrid vehicles by using range extenders.
Yes.
But yes, we agree that in heavy duty transport is where we see more and more application of this technology.
Yes. Okay, thank you. Okay, any further questions? Yes.
You work with a UPS using hydrogen as cells, and if you compare with a normal standard batteries, I think it's related to the Professor Humberto's question. You have to measure or estimate the efficiency of the conversion compared to the battery. The fuel cells that have more or less, how is the ratio of this conversion?
The efficiency, you mean?
Yeah, because you charge the battery and you put it back. And we can have
yes. So at the moment when you just use the UPS system on fuel base, we just tried with the PM system. There's efficiency around 40% from the PM system, but there are, due to catalyst investigations, there are much opportunities to increase this efficiency. So this is, I think, not at the beginning, but there is many opportunities to increase this efficiency. So there are many or some other types of fuel cells, like a SOFC system, a solid oxygen fuel cell system, but I think this is not possible to use it for the UPS system because it's worked at around 600 or 800 degrees. So that's not used, but the SOFC have efficiency around 60%. Yeah, the SOFC is used in apartment buildings for CHP systems because of the electrical high efficiency than the PEM system have. Okay. Okay, any further questions? Okay. Thank you.
Okay, so my name is Tahaguas Woldu, and I'm a PhD student and I'm a professor Wolter in the chair of the Electrical Power Networks. So I'm working on modeling and simulations of power system dynamics, and typically on integration of wind energy to the system, specifically to wind grid systems like the turbines, because I came from turbine. I'm just trying to analyze what is the impact if we increase wind generation of the system. So I'm working generally with this power system dynamics in the chair, also in different projects. So we are integrating in the simulation tools that we have developed in our chair, these different types of limited sources, and we are studying the performance, how we can optimize, and how we can create control modules that optimize the system performance. So the topics that I will go through are just, I will have an overview on this simulation tool, and also the control of the wind turbine, which is very common, the FIG type. And finally, I will have a specific topic on the frequency control mechanisms, or the capability of the wind power plants to control this frequency. So I will have an overview for the first two pointers, but I will have a little maybe details on the last one. So the problem with this one, with the motivation to start working with this topic is, yeah, of course, we all know that this inverter-based generationists lack to have control for their dispatching the generation power, and they do have also a problem with this inertia response, because they do have disconnected or decoupled from the grid system by this inverter, so we cannot have the inertia response. And the other issue is the rate of change of the frequency. So when we increase these renewable energy sources like the wind, then the drop-off normally increases, so that we have to have a capable to introduce a mechanism that we can enhance this virtual inertia, or we have to have some other mechanisms to remove this effects. And so the solutions normally are just implementing a voltage enhancement or regulation systems. This is actually quite matured now with these wind technologies. So the STATCOMs and other technologies are adopted to optimize or to regulate this voltage, so it's not a big issue. And the other is regarding with the active power control system that leads to the imbalance or problem with these frequency control systems. So in this specific topic, I will discuss how I have introduced an algorithm to control this frequency from the wind power plants, where the frequency change of the system is input to the control algorithm that we have developed in the control module. So this is a tool that we in the chair developed, and then which is normally used for dynamic simulation analysis, specifically for the RMS techniques. So we have an options with the conventional energy sources and the wind energy, and also there are dynamic motors, loads. So we include these impactors, and then you have on the other side the network systems. So this is a big system network, can work with thousands of buses, so that we cannot implement that one in practical. So we do have these simulations, and based on this simulation tool, we can evaluate the performance of the power system dynamics, and we can evaluate how the integration of different renewable energy resources are affecting to the system performance, so that we can initiate some control techniques to enhance this performance or optimization of the system. So we do this in MATLAB schooling as well as in MATLAB script programming, so that this is a tool that we are using for dynamic analysis in our chair. So this is that I can show you with the 9-bus Chp system where the rock-off have changed. If it was like all generators, synchronous generators, so the rate of change of the frequency is almost about 0.05 per unit. And if we increase or if we introduce generators from wind energy, then the lack of increases, so the rate of the frequency change is increasing because of this lack of inertia responses from these wind turbines. So this is the problem, then we have to come up with a solution to this one, and then this is actually for the synchronous generators where the output is increasing because of the load change. So the load change is increasing from 100 to 200 megawatts in this specific test network. And the active powers for the synchronous generators for the conventional is increasing, while for the wind it remains constant. We don't have this frequency control techniques for this wind power. So this is the problem, and the solution should be, we should have some mechanisms that our wind power plants can be capable of control these frequency changes, and or the wind power plants should follow to the grid in such a way that they can adjust their output power to be required by the network operators. So the issue is, here I have just put some blocks from Simulink, so that this tells how this control module in the wind power plant level is adjusting the control of the output power of the system. So the turbines are normally the turbines are made to operate in deloaded operation, and we have created a frequency control module which has an input of changing frequency from the grid system, and there is an input to this one, what amount of active power is demand or required to dispatch on this power plant, on the wind power plant, and then it's prioritized to those turbines which have high wind speeds, and then it gives a reference power to the group of turbines that are working on based on their operation ranges. So this active reference will be an input to the control. So we do have a control for the FIG normally in the decoupled control system, where the active power can be controlled and the reactive power can be controlled from the rotor side converter, so that we can have this reference power, which is dependent on the change of the frequency of the system, that is to be changed from the outputs. And from the system output, normally, here I just have the model of the wind turbine. So this diff is a change that is from the grid system, so that also the outputs from the algorithm that is developed for controlling or dispatching the wind turbines, then it will give a set of P references. Then this will be the reference for the inputs to the control system. So the first one is the rotor side converter, and then the second one is the grid side converter. We can have also another options normally by just having a drop frequency control on the back-to-back converter that can control the DC power, the DC voltage, so that we can also inject some powers on this one from storage systems or from other mechanisms, so that finally we can enhance the output power that goes through the rotor side. But this is actually limited to some 70%, so we cannot use this much to control for our system. So the first one is just controlling through this reference, P reference. And the operation of the wind turbines is according to this one. So there are wind turbines with wind speeds that range from 0.7. This is the starting rate of the wind turbine, the rotor speed in per units. And this 0.7 up to this one, we do have a linear relationship. And this is what we call the start of the wind turbines. And in this case, the wind speed is very low. So I was just rejecting the contribution of the wind turbines which are working on this one for frequency control. So the turbines that participate on the frequency control starts from B. So where B is a point where the minimum reserve or margin of the required can be obtained. So that from B up to C, there are wind turbine, one classical turbines. These are named as type 2. The first one is type 1, so it doesn't participate in the frequency control. Second one, type 2, which participates in the based on the amount of power. And the third one, these types of wind turbines also, this is a stage where the control normally, in this case, this is an optimal power. So the output power is dependent on cube of the wind speed. But if we just increase with these equations, so we will have a dramatic change on the output. So that normally for control purposes, but basically there is a relief time, a relief stage, where we can use linear change from this cubic to linear output, and finally you can have the rated generated power. So these three types can participate into the frequency control. And there is a method that we can prioritize these winds. The first one, we give priority to the first one, and then to the second, the fourth type, the fourth is the highest priority, the third one, and then the second one. And then the impact is normally the margin will have an impact on the this is the actual rate of change. So this is the group frequency controller. So our actual, so that will be just calculated from this linear relationship. And these parameters, the margin of the power will be dependent on the preference of the transmission system operators, as well as the frequency change of the grid system. So I just have the same type with the grid 9 grid system, IEEE 9 grid system, but I have just compressed. I'm just interested here with active power control with the frequency, and then the grid frequency is calculated by just the total generators that are included in the system, and then we have calculated the change of the frequency, where in this case there's the dynamics that includes the generator inertias of the all generators that participate in this system. And the first one type of the generators that participate in the participation is the third ones. So that the control gave an inputs, so 3 different inputs depending on the changing frequency that we have from the system. And then it gives prioritize to those with group 1, I mean with this highest output power or the high wind speeds, then it will give the priority to participate in the grid frequency control, and then the others with the, so just have included also a thermal power plant, but in this case I just reduced the thermal power plant to about 25%, not like the earlier one, and then 75% is just produced from the wind turbines. And I have also just neglected this one, and then I just make also to operate 100% of the wind turbines, and then some outputs are, I will just present to you some outputs from this one. So it's the same type with the earlier one. So these are the different types of parameters that I use in simulating these ones. This is specifically the just the control module. So here we have the algorithm, and in this case, I have the virtual inertia. I will include also the virtual inertia, and in this case, the output that is to be controlled, the drop frequency by the algorithm, will be an input to the drop frequency here. And then this will be have a gate zone with 0.2%, and then this output will be added to the reference, which is the deloaded output from the wind turbines. And then finally, it can operate for the output reference will be to the controller. So the idea is we have a wind turbine frequency controller module with an output of reservoir margins, and then from the actual wind power plant, so we have an output, and then we add up the change that we need to be adjusted to get the required frequency, and then this references will be the inputs to the control. Yeah, so this KSOs can be from the power system or from the transmission system operators. This can be suggested or set by these ones, and then the wind power operators, just they can have the power to dispatch which groups should participate in the power in this power, the frequency control techniques, and then that algorithm is doing this adjusting or making the wind turbines to participate based on their wind speeds into the system. So I just have here slide outputters just to check my models. So this is the total generation power we're comparing with the load. So the load is changed at 60. So there was some error in the imbalance in the beginning of the system operation, and then I just neglected that one, and then I start from the system, it's stable, and then at 60 there is a load change. So the blue color is the power generation that includes both the thermal power plant and the wind power plant. The wind is 75%. And then there is an oscillation because of this. I mean, there is a virtual inertia impact here also in the wind turbines. And then finally, the system will be balanced. So generation and the loads are balanced. So these are for the different types of the groups. So this group is the first one. I mean, those wind turbines that operate, or groups that operate at high wind speeds, and then they just participate normally in high in the frequency control techniques, and then dependent the others will participate also in the, according to the wind resource. And then when we look to the frequency, here you can see earlier it was like this. So now the frequency dropped to this one. This is in frequency in hertz. So it was about -2 to drop because of the load change, and then it returned back within some very short time, less than 10. So it returned back to its operation, so that we are able to control the frequency of the system change. And if we just make 100% of the weeks, that's what I have. Of course, the frequency change is increasing more than this one. Then, depending on the grid corridors, so that this is allowed, then we can also make 100% wind turbines. But of course, it increases to more than 2% or 2 hertz change. So these are the outputters, and then I just can complete from this one. The rock of is increasing when we increase the wind turbines to the system, and the wind power plants must include or must have. So they should indulge with these control mechanisms to follow the grid or to create the grid forming. So that we should have some control mechanisms to do this one. And finally, I just can say that the proposed algorithm module to control or to dispatch the active power on wind power plants is capable in just imposing these stable deloading operations. Yeah, so that's all what I can have for this presentation. Thank you. So, any question?
I will make a small question. You make the group control for injecting power on the grid or the wind turbines.
Sorry?
You use group control to share the current between the wind turbines, and then you have another control units that make the final tuning of the frequency regulation. That's far as I understand.
Yeah.
Because group needed some member to be active.
Yeah. Yeah, I mean, the idea is we have to have the drop frequency factor. What is that factor? That factor is dependent on the algorithm that we have seen. And then we just create the drop frequency factor. And then we use this one to decide how much change of power is required to adjust to get the change in frequency.
You change a little bit that they can overcome there.
Yeah.
Yeah, it's okay.
Yeah.
Okay.
Have you analyzed how this frequency control affects the energy in the long term?
Yeah, I mean, in the case of the wind, so as far as there is wind, the normal case is we have to generate the maximum power points. But if you, especially let me tell you in the experience of the Ethiopian case, when in the evening, in the nighttime, this the loads are decreased, and then there is high wind speed, and then there is a frequency change on the system. And then what's being done is they just shut down the wind turbines. So rather than doing this, it will be very good if you make the wind turbines to participate in the frequency control, and then just you deload them, and then they can stand themselves to operate for the system. Okay, thank you. Thank you so much.
Yes, welcome everybody. My name is Mr. Klabunde, and first of all, thank you, Professor Daniel, for the invitation here to UFSM, and also thanks to all of you for preparing all the program yesterday and also today. And yes, I will present today the topic of presentation that Marc Gebhardt has prepared, and that will, yes, handle his research topics from the last 1.5 years, so especially the power flow partitioning, or topic of power flow partitioning within the European transmission system, and this also with the effect of phase shifting transformers. Before I dive into this topic, also from my side, some small insights to Magdeburg. So Magdeburg is in the end a very historical city that was very large in the medieval age, and due to this also the name Magdeburg, that comes from Magdeburg, that's standing for powerful or mighty castle, came from. As it's next to the beautiful river Elbe, has 2 colleges, and from the medieval age or from the this medieval age, but from the historical buildings, especially the Magdeburger Dome, you can still visit when you are in Magdeburg, and you see also here on the bottom some parts of the old castle wall in Magdeburg. Professor Wolter already told that we have around 15,000 students in the University of Magdeburg, and additionally 5,500 students at the Technical College of Magdeburg, and this at around 240,000 people in Magdeburg, so it's quite similar to Santa Maria. If you look where the city is located, it is in the center of Germany, and when you look to the city from the perspective of the European transmission grid, Germany is then also the center of Europe. So having this in mind, and you see this large interconnected grid, some questions arise in the operation of this interconnected grid. So you have within the European transmission grid, and you have here this blue region is the region of Central Europe that is connected or interconnected with each other. We have a lot of different countries, a lot of different bidding zones that have own markets, and that will have also some flows through these different zones. So if you check here which types of zones you can have within the transmission grid, you have perhaps some balance zones. This is in this case here this blue zone. So you have 500 megawatt of generation and a load of 500 megawatt, and you have some unbalanced zones where you have a mismatch from generation and load. So for example, here zone B has less generation than load. So this is an importing zone that will buy some energy from the surrounding market zones, and you have zone A and B where you have more generation than load. So these are exporting zones that sell energy to zone B. When you will now, for example, look at zone C, that was a balanced zone, from a not interconnected perspective, you will see that the generation will directly flow to the electrical load and gets this power flow of 500 megawatt. Due to the fact that the maximum line or maximum power this line can transport, you will have no congestion in this case. So everything is fine, and this zone can be operated securely. But due to the fact that you have an interconnected system, you will have on this line that connects this generator and this load not only the power flow that is produced based on the zone, you will also have additional power flows. So for example, the generator here in zone B will also feed into this load in zone C and feed into this load in zone D. So you will have a higher power flow in this line, and also the generator here in zone A will also have a partial flow on this line in zone Z that is connecting this generator and this load. So depending on the circumstances in the grid and the connection of the different generators and loads and the market reside, you can have a line congestion on the line in this balanced zone, despite this zone is balancing its own loaded generation already. And yes, this problem is increasing in Europe due to the decentralized generation. For example, if you see Germany, where you have a lot of generation in the north and a high load in the south, especially this generation in the north will flow also through the other countries like Poland and Czech Republic. And due to this, the question arises, yes, who is paying, for example, for the congestion that will be introduced or will appear in these countries that this generation is not, or the generation is not produced and also the load does not exist. And due to the fact that this question arises, the power flow partitioning was developed, and the aim of power flow partitioning you can see here. So you have in the end different flow types. So you can in the end split the power flow on one line into these different flow types. So one internal flow means when you look at one line and the generation of this partial flow and the load of this partial flow are in the same zone as this line, it's an internal flow. A loop flow is the point I have discussed before. So for example, if you have the generation, for example, wind generation in Germany, a load in Germany in the south, so we have a flow from the north to the south, but you look at the line, for example, in Poland or Czech Republic, this is a loop flow because the source and destination of this power flow is in the same zone, so in Germany, but the line is located in another zone. Then from the market, if somebody is selling, or one zone is selling, or buying energy from another zone, we have import and export flows. And if, for example, the wind power in Germany will feed into a load in Czech Republic, and the power flow goes to Poland, we have a driving flow. So these are the typical market flows that we have here, and additionally, some other equipment in the grid, as HVDC links and phase shifting transformers, will produce additional flow types. So you can have internal phase shifting transformer flows. This is when the phase shifting transformer is located in the same zone as the line you're looking at, and you have loop phase shifting transformer flows. So due to the fact that the phase shifting transformer is producing every time a cycle flow, it will also interact with lines that are in parallel load zones of the transformer. Yes, and before I've asked the question, who is paying for this, and for example, which flow type of this yes, you have to pay for. And within the N2E, it's a little bit like this, that especially all the market flows, so internal flows, import and export flows, and transit flows, so that are allocated directly to the market, are seen as good power flow types. And especially loop flows, because they interact with a zone or with a parallel zone that has not the generation and load that is based on the market result, are seen as bad flows. And we a little bit have the view that this is not very good, because we have an interconnected system, and especially this interconnected system has also a lot of advantages. For example, that you have higher inertia in comparison to the presentation from before, and that you can operate this interconnected system in a more secure way. So it will be more realistic that in the end every flow type will be paid equally. So because it's so that you have these different flow types as a result of the many advantages of the interconnected system. So also everybody should pay for the different flow types that arise in line. Yes, so what we have done in the last 1.5 years related to this topic is we have compared different algorithms in the literature from power flow partitioning. So that is especially the power flow coloring method and the full line decomposition. Then we have developed an own partial power flow method, the power flow decomposition, that in comparison to the other approaches before did not make DC assumptions that will handle directly with the AC power flow. Then we have included also as HVDC links or HVDC systems into these power flow partitioning methods. And we have included phase shifting transformers in the first step by the direct current phase shifting distribution factors. So in this case, with this KSDF factors, we again have some DC assumptions that we have to assume to calculate the effects from phase shifters in the grid.
And the thing that Marc did now is to implement an approach to calculate the effect of phase-shifting transformers without the DC assumptions to consider the whole AC power flow. And the general idea behind this is, if you have a phase-shifting transformer that is between two nodes in the grid, you can neglect, or you can in the end, when you have this phase-shifting transformer, you have the overall power flow over this line, and this is superposed or added by a current that is only deduced or only created or is only, or where the source of this current is the phase-shifting transformer itself. So the idea is to neglect this phase-shifting transformer, but represent it by two current sources on the two nodes the phase-shifting transformer is connecting. So that we have, due to these two current sources, the same effect as before, and can then superpose all the currents of the system with the current of the phase-shifting transformer. So as you can see here, in the end, based on the voltage difference between the two nodes that is created by the step of the phase-shifting transformer, you can calculate these current sources, and then you can superpose the currents of the whole grid and the currents that are created by these additional current sources, and calculate based on this the effects that the PSTs will have on the overall grid. And due to the fact that this whole approach is done in unit values, you have to recalculate then the currents into ampere, and can then define the current that is deduced directly by the phase-shifting transformer. Yes, so to conclude this, yes, we have developed some methods to calculate all partial power flow types based on AC power flow assumptions, based on this phase-shifting transformer approach and the partial power flow approach, power flow decomposition. Then we have compared our results with the new approaches with the discussed DC approaches, so the power flow coloring and the full line decomposition, and see better results in all of our approaches. And the next steps now will to discuss. So we have done this project with one transmission system operator in Germany. So the next is to discuss these approaches also with other transmission system operators in whole Europe to see which method or which model has the most advantages. And that should stand for Marc's dissertation. It's in the end to create based on the shown shown approaches to calculate, let's say, phase-shifting transformer sensitivity matrix, which is defined here as a PST Jacobian matrix, to afterwards integrate this Jacobian matrix or the sensitivity matrix in optimization algorithms to find optimal places and optimal operation points for phase-shifting transformers. Yes, so obrigado pela sua atenção. And if you have any questions, please ask.
PST is a complex asset in the European Union.
Nowadays, it becomes more common here. So there are already some phase-shifting transformers installed at the border between Germany, Poland, and Czech Republic, and it can also get a more common asset to build between transmission system and distribution system to also control the power flows through the distribution system and to use the system in a better way.
Can you show the map?
Yes, it was slide 3 or 4. It was. So one you can say that it's wrong, but one PST is installed here.
Ist Hamburger Nikolova?
Yeah.
The Ost, there's number one Kalifirma.
Yeah. So here are two over here, efficiently controllers.
Worst of Alec is the third.
Yeah.
Between Germany and Czech Republic.
Yeah, so also continental Europe is the same frequency.
Yes.
Yes, yeah. So I've shown this figure, so this blue region is operated with the same frequency. Yeah.
It's one of the
Yeah. Yes, it's very different to the system in Brazil, where we have a lot of HVDC links between the different regions in Brazil, and they have the same frequency, but another synchronous frequency. Yeah. Okay. Okay. Thank you.
The left HVDC lines.
HVDC lines. You know.
There are HVDC lines between different colored regions you see there in this figure. And also the additional HVDC line within the blue region in Germany. There's already one between Germany and Belgium.
So thanks a lot, Professor Martin and the students. I really loved the presentations. Some questions or finish the session. It's okay, então thanks a lot, people. After put the links to YouTube record all of the presentations in the website of the PTF. Thanks.